Mr.Chege. Today I'll be presenting to you the unit Basic Mathematics, BMA 1111, and mathematics is a subject that deals with numbers, and therefore in the first lesson I'm going to introduce to you types of number systems that will be used in mathematics. We have different types of numbers. We have whole numbers, we have decimals, we have some other numbers that have terminating decimals and others that have unterminating decimals. So all these are put into classes, and these classes form what we call number systems. So the simplest form of number systems is called the natural numbers. And you can see that number system just involves numbers that are used in mathematics there. Now, a natural number, these are positive whole numbers. Positive whole numbers, that set that contains positive whole numbers in mathematics, they form the set of what we call natural numbers. Symbolically, we use the symbol n to represent the set of natural numbers. This can also be represented this way: 1, 2, 3, and so on. So we are saying that all natural numbers will start from 0, 1, 2, all the way up to infinity, but not including infinity. And therefore, n can also be represented as including 0, but excluding infinity. This representation is also the same as this representation of the set of natural numbers. So these numbers are also known as counting numbers. You know, if we were to consider a situation where we are counting ownership of things, then if someone doesn't have anything, then in the number system we place that person at point 0. If that person has 2 items of what we are considering, like say animals, we are in a situation where we are to count the wealth of people in terms of the animals that they have, like say cattle, then if someone has 4 cattle, that we say that person has a wealth of 4. So that form of counting, that it is what that takes us to calling the numbers counting system, because basically they were introduced to enhance counting in mathematics. Now the other set of numbers is integers. Consider a situation where we are looking at a number of goats people have in the compound, and someone has taken their goats to a friend's so that they can be there for some time, maybe for some reasons. So when we go counting those animals, then where do we place a person who has animals that they don't own? Or for instance, if I have borrowed 2 units of money from someone, and another person has 3 units of their own money, you know, or rather if I have borrowed 2 units and another person has 2 units which are of their own, then me and the other person, we are on the same level. So integer number system is there to count or to involve situations where someone are on the opposite side of what we expect in the number system. So that if I have borrowed 2 units of money, then I am in the category -2. And if the other person has 2 units of money that they own, it's theirs, then they are the point 2 in the integer number system. Actually, the integer number system can be represented in the number line such that this is 0, -1, -2, and so on, and then this is 1, 2, 3, and so on, all the way to, but not including infinity. Now, the other form of number system, and before we go to the other form of number system, we call these the set. We say that this set is infinite, because in this representation of this form, you can see that it contains an uncountable set of numbers in an open interval from 0 all the way to -infinity, and from 0 all the way to positive infinity. Then we have another class of numbers. We have what we call rational numbers. A rational number is a number that can be represented in the form of mn. That is, if I have a rational number, say p, And I can be able to write it in form of two integers, say m over n, then this number is called a rational number. If a number, say r, cannot be written in the form of m over n, then this number is called an irrational number. Now, this form of representation of numbers works specifically if the value of b is not equals to 0, because if we have 0, b being equals to 0, at that point, then we will have that fraction being undefined, and therefore we restrict that b cannot be equals to 0. Now, the common divisor between a and b is 1. For this representation to work, then the divisor between a and b has to be 1. That is, we are saying if we have p being represented, then we would pick something like 3 out of 5. But picking a fraction like 4 over 6 would not conform to this requirement. It only works for situations where these two numbers, the numerator and the denominator, do not have a common divisor, and the only existing common divisor is then 1 if it exists. Now, the irrational representation, we are saying that this number, if it is irrational, it cannot be represented or written in the form of a over b. So if there are not two integer numbers that you can write to represent a number, then that number is irrational. Examples of irrational numbers is mostly the surds. A surd is a number that has an unterminating decimal. So root 2, root 3, root 5, even root 12, but you notice that the square root of 12 can be simplified, because this can be written as the square root of 2 times 3, which is, or rather, sorry, 4 times 3, which is the same as the square root of 4 times the square root of 3, and this is the same as 2, the square root of 3. But this simplification does not make this number not to be irrational, so it's still irrational due to the square root of 3 part. Now, let's look at real numbers. Now, real numbers are numbers that can be represented on the x-axis of the Cartesian plane. Now, if you have a Cartesian plane, the representation of the x-axis is such that this is the point 0, this takes negative form of numbers, this takes positive form of numbers. This is called the x-axis, and we also refer to it as the line y is equals to 0, because this being the y-axis, then at this point along this line, then the value of x is 0. This being the x-axis, then along this line, the value of y is 0. So that any point above this, you get positive values of y. Any point below this, you get negative values of y. So all numbers that can fall along this line, they are the ones we are calling the set of, they are the ones we are calling the set of real numbers. And the representation or the symbol form of the set of real numbers is R. And equivalently, we can write these as the open set from negative infinity to infinity. These two mean the same thing, but we do not include infinity, because infinity here means undefined. So we are considering all numbers to the negative side and to the positive side, including 0, that are defined. So we exclude the undefined part of the real set of numbers. Now, the set of real numbers means that we have combined all the number systems that we have. The set of real numbers R consists of natural numbers. Then it also consists of the set of integers. And then it also contains the set of rational and the set of irrational numbers. So the composition of this then takes the whole set of number systems that we are going to use in maths, but it is a procedural increment or change from one set of numbers to the other, because we notice that in the set of natural numbers, we were talking about 0, 1, 2, 3, all the way to infinity. In the set of integers, then, we included negative part of the number line. Then, in this one, we said it's numbers that can be simplified in the form of a over b. And in this one, they are all numbers, including those cannot be converted. So, this growth takes you to the set of all numbers that you will meet in mathematics. And therefore, the set of real numbers is the superset. It is a set containing all the other sets that we have discussed of all the number systems. Then we can look at complex numbers. At times, you have to work with numbers in mathematics that will form the set we call complex. For instance, look at the square root of a negative number, say 5. Now, it is not possible to evaluate the square root of a negative number, but then it is possible to represent this number such that it has a real number part and a complex part. To do that, we introduce I to this number such that this number is written as I, then square root of 5. Now, I here is the square root of negative 1. So, the number representation, the representation of the square root of negative 5 as I square root of 5 is said to be representation of a number in complex form. Of course, we'll have a lesson for complex numbers. So this is the set of numbers which can be written in the form Z is equals to I A plus IB. So what we are saying here, if we write negative 5 as a complex number in the form of Z is equals to A plus IB, then we'll say square root of negative 5 is the same as 0 plus I square root of 5. And you realize that now it is possible to get the square root of this number, unlike the situation where we had this. So representation of negative 5 in form of Z will be 0 plus I square root of 5. And this now takes us to the definition of an imaginary part of Z, where, as I was saying, this I now forms the imaginary part of Z, where I is negative, is the square root of negative 1. Now, let's look at recurring decimals. Now, recurring decimals are numbers or fractions which, when divided, they result into a number after the decimal that keeps on repeating itself. So these decimals have an endless recurring number after the decimal point. Recurring examples include 4.222 and so on. So the 22 will keep on repeating to an endless point. Then we have 0.32. You can see that two numbers are repeating in this case, 32, 32, and so on. Now, recurring decimals can be expressed as rational numbers. That is, as I was saying, most of the cases you find that these numbers are a fraction that, when divided, ends up giving you such a result. So a fraction, a rational number, we've said, is a number P that can be represented in form of A over B. So we are saying we can be able to represent the recurring decimals in this form, such that it has a numerator part and a denominator part. Now, let's look at that example there. We want to express 1.2727 and so on as a rational number, or in this case as a fraction. So what we'll do, we let n to be the number we want to change its representation. Then we attempt to move this decimal to a number of steps that will make the part that is being repeated move to the left of the decimal. You notice that would imply me shifting the decimal 2 places. To do that, we use the 10 to power n representation, where n is the number of steps that I'm carrying, so that I shift the repeating part to the left of the decimal point. So in this case, 2 steps. So I need 2 10 to the power 2, which is 100. So by multiplying this number by 100, I'll be able to shift this decimal into the left side, such that the decimal will just be after this 7. But if I have to do that on this side, I also have to do it on this side. And therefore, if I multiply this by 100, I get 100n. And then by multiplying this by 100, I shift it, becomes 127. Now 27. Remember, this keeps on repeating itself. So if I bring this down here, then I'll have 1.2727 being repeated that way. And now, if we attempt to subtract the 2, this becomes 99n is equals to 126.0. You notice that each of these cancels up to wherever it goes. So the part after the decimal disappears in both cases. So we have then n is 126 divided by 99. And you notice that this can be simplified by 3. This becomes 42. By 3, this becomes 33. And a further simplification, I think by 6, we have 7. By 6 we have 7. Or rather, we can go by 3, so that we have 1 and 4. And then by 3, we have 11. So we have 14/11. This fraction, if divided by long division, is probably going to give us what we had over there. So we found that the representation of the recurring decimal is 14/11. So we can check whether the long division of this will give us the same recurring decimal as we had there. It goes 1 time because of 11. We have 3. We put this decimal, so we are allowed to put a 0 there. Then this goes twice because of 22. This is 8. We can put a 0 due to the decimal. It goes 7 times, so that this is 77. We have a 3. So put a 0. It goes twice because of 22. You can see that this will keep on repeating, and therefore the representation, the rational number representation of the recurring decimal is 14/11. Let's look at a theorem here. The theorem says that the square root of 2 is irrational. We need to prove that 2 is irrational. But the proof we do here is based on a rule called the contradiction method of proving. So we will first assume that this square root of 2 is a rational number, and then we show that this is a contradiction. When we show that this is a contradiction, then the previous statement is then true, because we have contradicted what we have already had. So if a number is not rational, then it's irrational. So if we prove that saying square root of 2 is rational, then we'll conclude that it has to be a rational number. Now, the square root of 2, if square root of 2 is a rational number from the definition we've had, then it means that it can be written in the form of a over b. Now, let's square both sides of this equation. That will mean that we have the square root of 2 squared being equals to a over b squared. So that we have this root cancels with this, so that we have a 2. Then this is a squared all over b squared. Now, that means that a squared is equals to 2b squared by cross multiplication. And from this, if we label this as equation 1, then we are saying that for any square numbers written in the form of 2a squared is equals to 2b squared, then a and b, or a squared and a, must be divisible by 2. And in fact, we can illustrate with an example. Then let a be equals to 2 and b be equals to, say, 1. So if 2 squared is equals to 2 times 1 squared, then it means that this result, which is 4, is divisible by 2. You see, 4 is equals to 2. This 2 makes sure that any result we get for squaring a has to be divisible by 2. In fact, even if we interchange and have a is equals to 1 and b is equals to 2, then, or even let's have all of them being odd numbers. So we'll have 1 squared. You see, 1 is not divisible by 2, but check. If I use the transformation 2, then 3 squared, then you notice that my a squared from the right-hand side becomes a number that is divisible by 2. And therefore, this means that for this to be true, a squared must be divisible by 2, and the result of 2 times b squared will always be divisible by 2 due to these 2. That's a contradiction, because we said that our rational number is such that whatever numbers we put as a and b should not be divisible by any other number other than 1. Now, look at this. We have a is equals to 2p from the representation of p is equals to a all over b. And if we substitute here, then we get that if a is equals to 2p, then if we square this, we have a squared is equals to 4p squared. Now, this representation then means that if this is a new definition for a, then a squared, we can equate the two sides of equation 1 and this one, and then because we had a squared is equals to 2b squared, and then we've had that a squared can also be written as 4p squared. Now, this representation means that 2b squared is equals to 4p squared. So that we have b squared is equals to 2p squared. Then let's have the representation 2 is equals to 2p squared. b squared and b have to be divisible by 2 for this property to hold. And therefore, again, we have a contradiction from what we expected. Assuming that is rational, this is a contradiction, because we are having that 2 is another common divisor between a and b, and therefore it contradicts this statement of a number being rational, and therefore square root of 2 must be irrational. Another theorem, let's have a different number representation, square root of 5. We want to check whether, we want to prove that root 5 is irrational. We'll do that by contradiction again. So we first assume that square root of 5 can be written as a rational number, m over n. Now, if 5 can be written that way, by squaring both sides, we have 5 is equals to m squared all over n squared. So that we have 5n squared is equals to m squared, just like in the previous case, and we can label these 1. So in another representation, from 1, m squared and n and m itself must be divisible by 5. Let, again, m be defined by 5k, because we've seen that m is a multiple of 5. So we have m squared is equals to 25k squared by squaring both sides. And therefore, we can say that 5n squared is equals to 25k squared, which actually implies that n squared is equals to 5k squared. Again, 5 becomes a common multiple, which is a contradiction, and therefore square root of 5 must also be an irrational number. That is the representation of number systems we are going to use in mathematics, and forms our end of lesson 1.
We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.